sleep. Why? I don't have no idea. Summer schedule. Waking up at 4 in the morning.
It's a forest.
And where were you in Boston?
Literally right in the back bay of Boston. So it's pretty nice. There wasn't so much traffic getting in there or getting out.
You put some strangers' earbuds in your ears.
I mean, I was gonna clean them first.
Counts.
I mean, there's probably the worst stuff. What, Willie? No. This is gonna be us.
Give a piece more.
Nice bucks. What about you? Huh? Is it, it's not for Cold War? I was looking at that like last night. It's on. Little worse. You caught crossbar over here too, yeah. What is it, $60? Yeah, $80, $50. Yeah. You could probably swing. Is this obvious one? You put it in.
It's definitely cool. That's not true.
Yeah. Everybody can get this one.
Okay. Assume that everybody can hear me. If you cannot, please respond in the chat room so people can see that. I see a thumbs up, that's good. Are there any questions from last time about what we developed for energy? Again, that was all theoretical. Now we're moving into application of what we just did. So you just check that the chat camera is tracking me. Should be. So what we did last time again was develop what we would call the energy equation or the energy relationship. And that what we did was we started out with a differential element. We identified that we could connect a fluid path line, and with that fluid path line on anywhere on that fluid path line, from point to point to point to point, the sum of v squared over 2g plus p over gamma plus z, velocity, pressure, elevation, is a constant. And we call that constant the Bernoulli sum. Question?
Can you put the screen down?
I can.
Thank you.
That is something I can do. Much better. Thank you. I usually don't look at that. For those components, again, the first 5 or 6 slides are the same slides from the end of last class. We're just doing a review. So the Bernoulli sum has the dimensions of length, and that's the total energy at that specific point in the fluid. The first term, velocity squared over 2 times the acceleration of gravity, is kinetic energy. We call that the velocity head. And V is the average fluid velocity. And how we get that is by taking the total discharge and dividing by the area. Conversely, we could use the energy equation, for example, to calculate discharge. And in that case, we would use the energy equation to calculate the velocity, as you'll see in some of the examples. The P over gamma term is an old friend from fluid statics. It's identifying potential energy. And again, gamma is what differentiates or distinguishes fluids. Obviously, if you have the same pressure with different specific weight, it gives you different pressure heads. And then Z is, again, potential energy. And now we're just talking about the elevation of the specific point of the fluid on that path line that you're talking about. So in general, right now, V is constant. In the future, it will not be. And we'll see some of those changes as soon as next class. As long as you have a continuum and you can draw this path line, anywhere on that path line, the Bernoulli sum is a constant. If the fluid is moving, do not expect fluid statics to be operative. In some cases, it appears as though it is. And that's just because right now we're saying that the total Bernoulli sum is a constant. In the future, that's not really true anymore. So P is equal to gamma H is not in general operative, but as I showed last class, if you happen to have a fluid that's static, that static condition is a subset of the general energy relationship. We also introduced grade lines. So the sum of those 3 components of energy, we call the energy grade line. And if you can calculate these 3 components at any point in a fluid, you can trace out that sum, and that sum is known as the energy grade line. The sum of just the potential energy components, pressure head and elevation, are known as the hydraulic grade line. And when you're doing designs, you typically have to show one or both of these in your designs for your systems. In a single pipe, these are just lines, but we do this for entire distribution systems. So it's basically a surface over the entire city where we're plotting this out. So here is a very simple figure of what's called a venturi. And you'll be studying these in 2 labs in this course. And what happens is flow is from the left to the right, as you see. And with this flow being left to right, you are going from the original cross-section of 75 millimeters into the smallest cross-section, what's known as the throat of the venturi. So what you've done is dramatically decrease the diameter. If the discharge is a constant, then what's happening is the velocity is getting much larger because V1 is Q over A1 and V2 is Q over A2. And because the diameter and therefore the cross-sectional area decreased significantly from 1 to 2, the velocities had to increase. And as I showed last time, what's happening here is that you start to do energy conversion. So you'll see I drew this green line through the center line. That's Z. So I can draw a path line right along that center line, and at any point along that path line, Z is equal to the same value because it's a horizontal line. And in fact, very often, you have the capability to identify the elevation datum in your problems. So in a problem like this, I'd say, I'm just going to let Z equal 0 right on the center line. And I might analyze, for example, a point here and a point here. Or actually a point here. Why did I pick those two very specific points? Well, this barometer is something that you've studied before. With a barometer, we used fluid statics. And you could calculate, for example, either the pressure at A or the pressure at B, or in this case, the difference in pressure between A and B. So that barometer is giving you information. And you can use what we knew from fluid statics. Why? Well, this manometer is static. The fluid's not moving in the manometer. So you apply fluid statics to a manometer. Another way of showing this could have been just two pressure gauges at these same 2 points. And the difference between the pressure gauges is the same difference that the manometer would be giving you. So when you see a manometer, it's telling you something about pressure or pressure difference. The other thing is we drew Z and I drew the EGL, which is the dashed blue line. How did I draw that? Well, I don't know exactly what it is, but I know that wherever you go on that path line, the energy sum, V squared over 2G plus P over gamma plus Z, is the same. Horizontal line. Now, what's different between these two, as we just showed, as we move downstream to the throat of Venturi, the velocity is increasing. And so what we can do is subtract the velocity, or the velocity at squared over 2G, from the energy grade line and trace out the hydraulic grade line. So if we do that, you'll see this red line. And so what's happening is we have an initial velocity head, V1 squared over 2G. And then when we get into the throat, you can see that that's increased because continuity says the velocity has to increase. Well, what is the difference between the hydraulic grade line and the elevation? So the dashed red line is the hydraulic grade line. The dashed green line is Z. HGL minus Z is P over gamma. So what you have is this term is P1 over gamma. And in this case, P2 over gamma is physically below the pipe. Can that happen? I've said this thousands of times in here, it seems like. You've all had this experience. You've all done this in your life, but you've never put algebra or math to it. I'm sure most of you have used a straw. This is what's happening in a straw. In a straw, you have negative pressure. What's happening when the hydraulic grade line goes physically below the pipe, you have negative pressures in the pipe, and that can certainly happen. There's nothing wrong with that. So what you did in this case was you converted P over gamma to V squared over 2G. And so you stole energy from potential energy, the P over gamma, in order to get the velocity high, the velocity at V2. So that's why the hydraulic grade line, energy grade line, and Z all look the way they do. They're all representing their individual forms of energy. Expect to see a homework problem on this. Expect to see it on exam 2. Expect to see it next semester. Okay, so for energy problems, again, we trace out a path line. We can select any points, as many as we want. Here I selected 2, point 1 and point 2 on the path line. And what we say is the total energy at point 1 is equal to the total energy at point 2, is equal to some number. It's a number at the end of the day. and it can be a positive number, and it can be a negative number. The energy grade line can be below the pipe. Assuming you know G, the acceleration due to gravity, and the specific weight of the fluid, we have 6 unknowns in one equation. So we either need 5 other equations to solve, or we need a combination of 5 other equations and boundary conditions, known variables. Yeah.
When would the energy grade line be below the pipe?
I'm sorry.
When would the energy grade line be below the pipe?
I was going to get to that, but since you asked the question is, when is the energy grade line below the pipe? Glass of milk, okay? We're going to call our elevation datum right at the free surface. You can call it wherever you want. I'm putting it at the free surface. What is the pressure at the free surface? 0. Now, we haven't gone through this thoroughly. It's on one of the next slides. I did present this last time, but for your glass of milk, there's really no velocity in it, okay? So where's the energy grade line? What is 0 plus 0 plus 0? 0. So not only is this z equals 0, it's the energy grade line, right? The energy grade line is the free surface. And actually, you need to use that as an important knowledge point. Whenever you see a large body of fluid that has a free surface, you are looking at the energy grade line. So now we're going to put a straw in here. And we're going to draw fluid up, okay? So you know how a straw works. I don't think I have to explain it to you. But when I have fluid here in the straw, fluid's moving in the straw. So we have a velocity here, some velocity. And so what's happened is we've created, at this point, v squared over 2j. And so EGL minus v squared over 2g, this is now the HGL at that point. What will happen if you can accept this? Let me escape. And then insert a slide. And go back to presentation. So now what we're going to have is a pipeline. And here's our EGL. Western Colorado. And here's Denver. And they want to plumb the water, and they have to get over the Rocky Mountains. So the pipe do this. And so what you see is if the energy grade line stays constant, the pipe is going up above the energy grade line. Is that a problem? No. The straw does this. This pipeline does it. What is the limit? Again, the limit is always the vapor pressure. How do they really do this? We're going to talk about mechanical energy and pumping next class, but that's how they move water around. So that's probably the easiest way to explain it. We can always move the pipe around, and the energy grade line is what the energy grade line is. The problem with a system like this is it's a fatal flaw system. This is spinach for the brain. If you have one hole in that pipe, have you ever tried to use a straw with a hole in it? Try it sometime. It won't work. What happens is air will enter this system when you have a negative pressure, and that blocks the flow. So we usually do not like negative pressures in our distribution systems. They're not very helpful to us because of that fatal flaw. It's almost impossible not to have leaks in pipes. I was talking to the operator of a community system of 270 people up north on Lock Lake. And they have about 18% leakage, unaccounted for water. So they know how much water they're putting into the system. If you divide that 18 gallons a minute by the 270 users, it's hard to measure that. So there are things that are beyond our capacity when we're designing systems. You're kind of foolish if you design negative systems, negative pressure systems. Do we do that sometimes? Absolutely. So for example, vacuum sewers, we actually will design negative systems. And it has everything to do with how we're manipulating the energy grade line in all of these systems. Okay, so this again is slides from last time, and I'm going to do examples. I'm just reviewing and reminding you of all this. How do we solve these problems? First off, how do you know it's an energy problem? That's the most difficult, challenging question you'll have. Well, is the fluid moving, or is there relative motion? If there is, energy is involved. Even if the fluid is not moving, static systems are a subset of energy. So you're basically still using the energy concepts, but fluid statics is a subset. In order to solve the energy problem, though, you may need continuity or some other equations that we'll be getting to. So the first thing you want to do is sketch the system. More often than not in this course, whether it's an exam or a homework problem, you'll be given a sketch. In very rare cases, you'll be just told, well, you have this horizontal pipe. If you just have a word problem, sketch it, sketch the system. It helps you and it helps us grade your work. And when you leave here, it will also help people review your work. After you've sketched the system, make sure that you can draw the path line between the points of interest. Once you've done that, identify the known variables and all the different pieces or components of the system. And again, I gave you a list of these known variables last time. And then the fourth thing is you need to, for me, always show the elevation data. When you leave here, you may be working in, for example, the National Geodetic Vertical Datum, 1988 NGDD, and all your elevations are in a relative datum, but we know what that datum is. If you're using a local datum, like I did in the previous problems, you need to show us where Z is equal to 0. My guidance to you, if it's possible, always set that datum at the lowest elevation of your problem. Then you always have positive elevations. If you set your elevation datum where Z is equal to 0 high and you have components below that, you just have to remember you have negative elevations. And that negative sign typically somehow gets lost when you're doing problems. 5, identify the desired variable, the unknown. What are you after? Select points for the energy analysis, doing an energy balance. 1 point's typically where you know information, and another point is where you're trying to calculate information, the unknown variable. And then lastly, apply and solve the energy equation for the points of analysis. You're going to see these steps again. So I'm going to do an example and we're going to reiterate these exact 7 steps to show you how I'm doing it each time. When you're doing problems in here in this chapter, you should basically be following these 7 steps. Okay. So this was, I think, where we ended last time. Where do we pick points? There is guidance for where you pick points. Any free surface. So the example I just gave you before with the glass of milk, free surface, we know the pressure is 0. And that can be the free surface of any fluid in any of these situations. I think you understand what the surface of a reservoir is, the surface of a river or a stream. Free jet, we're going to do in the next example. I will explain what that is. The surface of the groundwater table, or surfaces in vented tanks. All of these have atmospheric pressure. We work the problems in the gauge pressure datum, and therefore atmospheric pressure is 0. 0 PSI, 0 feet of mercury, 0 Newton per meter squared, whatever dimensions you're using, it's 0. The other thing you look at is when you have very large volumes of fluid, there's fluid moving compared to small cross sections. In the large tank, the velocity is almost zero. And therefore we assume that when we have large volumes of water in systems where fluids are moving, the velocity head, v squared over 2g, is basically zero. It's negligible. Your pressures or pressure differences are given. So if you see a gauge giving you pressure, or you see a manometer or a barometer, that should be one of your analysis points. Why? You're given information. Remember, we have this one equation with 6 unknowns. So you want to select points that help us solve that equation. And it may not solve the equation exactly where you want it, but each time you pick a point, you may be picking up more and more information that you know. So in one problem, you may have applied the energy equation 3 or 4 times. Each time you're picking up a variable you need. And again, gauges, manometers. And then lastly, where you know elevations or elevation differences. So you'll see this as a common theme in a lot of these problems. Where you're given information, that's where you should usually select points. So I want to look at a very simple example, and I'm sure conceptually you can understand this. We have this big tank, and some little kid walked up to it and poked holes in the sides. And what you would see is these free jets. Why is it called a free jet? Again, it's a hole in the side of the tank. So there's the hole in the side of the tank. And what's happening is fluid is shooting out the side of that tank. Once it escapes the boundaries of the tank wall, the pressure all around that jet is atmospheric. That's a free surface, right? And what we typically assume is that the pressure distribution throughout the free jet is also then atmospheric. Not exactly true, but for engineering applications, it's a good enough assumption. So again, the pressure, for example, at the center line of the free jet is atmospheric. Pressure at the edges, the outside surface of the free jet, it's zero. So in the previous one, I identified what that free jet was, and that's a point of analysis for you. So we're going to look at just one of these free jets. Again, hole poked on the side of the tank, and we want to apply the energy analysis. First thing we do is sketch the system. That's what you see here. The next thing we would do is identify or trace a path line through the system, connecting points or of interest or analysis. So again, basically you see that, you could do this anywhere, but fluid is basically flowing from the tank into the free jet. And we can pick any points along a path line and say that the Bernoulli sum at one point is equal to the Bernoulli sum at another. The issue or the importance of the previous slide was there is a judicious selection of the points. You want to pick points where you know information. We're going to identify the known variables. So for example, in this one, let's say you're given H. We're given the orifice diameter. So that hole in the side of the tank is known as an orifice. We're going to set and show the elevation data. So, I thought I put it in there. Let me just go ahead because I thought, yeah, there it is. So here I'm putting at the center line of the free jet, Z is equal to 0. That's my elevation data. So that was step 4. Step 5, identify the desired variable, the unknown. In this case, let's say we want to know what is the discharge Q from the system. Now, if we wanted to, I think I have that on here. We could just apply continuity, right? Just like in the cross section of a pipe, just like you did in the fluids lab, discharge is velocity times area. Well, we don't know the discharge and we don't know the velocity. So continuity doesn't help us. It's maybe a step in the right direction, but by and of itself, continuity doesn't help us. However, what we could do is look at this as an energy analysis. So this is the same problem, but now step 6 was select points for an energy analysis. One point is typically where you know information, and other points are where you may also know information, but it's where you want to calculate information. What do we want to know? We want to know the velocity of the water leaving that orifice so we can use continuity to calculate the discharge. So again, this was the previous slide. Judicious selection of points. Do you see a free surface anywhere in this system? Of course you do. At the top of the tank and the free jet. So we have this and we have this. So those would be two locations that should pop off of the paper at you that would say, pick me. These are two analysis points. We also have a large volume of fluid. And again, what that means is the velocity is going to be approximated by 0 if we pick a point in that large volume of fluid. There's a caveat with that, and I will give it to you. And we also have this. We know that the free surface is H above the center line of the free jet. And we'll see that in the next slide. So this is where we were before we just had that interim slide. And we want to pick some points of analysis. What are we after? If we can get that velocity, then we can use the continuity equation to get the discharge. So let analysis point 1 be at the free surface. Here's point 1. Let analysis point 2 be at the center line of the free jet outside of the tank. Never pick point 1 here. You will be seduced into thinking you can use fluid statics, that the pressure is there as gamma H. It is not. Okay. At the free surface, we do know what the pressure is. In the vicinity of that orifice, you have velocity, and therefore you do not have atmospheric pressure anymore. So I don't want to see anybody saying point 1 is horizontally across from the orifice. That's not good. So point 2 is going to be at the center line of the free jet. And what does that mean? Well, we're going to use an energy balance. And we're going to say that the total Bernoulli sum, V1 squared over 2G plus P1 over gamma plus Z1 is equal to the Bernoulli sum at 2, V2 squared over 2G plus P2 over gamma plus Z2. And again, throughout the entire system, that's a constant. So just like the glass of milk, are you looking at the energy grade line anywhere? Right here, right? So this is, as you're going to see, the energy grade line. And I'm going to give you a spoiler alert. At point 1, we're holding all of our energy as H. At point 2, all of our energy is V squared over 2G. We did an energy conversion. Did anybody do that today? It's what happens when you open a faucet. Behind the faucet, all of the water is stored as P over gamma. You open the faucet, you convert it to V squared over 2G. You probably do this dozens of times a day, thousands of times in your life, but you never knew that's what you were doing in energy conversion. That's how we design distribution systems. We store the energy as best as we can as elevation or pressure, and we convert it to velocity at the very last minute. And the reason why is all energy losses are a function of velocity. The higher the velocity, the more the energy losses, as you'll see later on in this semester. So at point 1, we know the velocity at the free surface in the big tank is approximately 0. Free surface, atmospheric pressure is 0. The elevation of point 1 is H above our elevation datum. Our elevation datum is the center line of the free jet. At point 2, which is the center line of the free jet, we don't know the velocity. It's a free jet, so we have atmospheric pressure, and so P over gamma, or P2, is 0. And Z2, we judiciously put the elevation datum right at point 2. So that's 0. So if we, again, start with our energy equation, that energy equation is identifying the energy components at each point. And now we're just going to insert each one. V1 squared over 2G is 0 because V1 is in a large tank and V1 is very, very small and therefore negligible. P1 over gamma, well, we have a free surface at 0.1, so you have atmospheric pressure. P1 over gamma is 0. And Z1 is H. And so everything on the left-hand side just boils down to H, which again, that's the energy grade line. That's what we drew on the last figure. And that's equal to V2 squared over 2G, which we do not know. That's what we're actually using the energy equation for. P2 over gamma, since it's a free jet, P2 is atmospheric, so it's 0. P2 over gamma is 0. And Z2 is right on the elevation datum, it's 0. So you're left with B2 being V squared over 2G and B1 being H. Again, at location 1, you're keeping all of your energy as elevation. At point 2, you've converted all of that energy to velocity and to kinetic energy. So the result is this boils down to H is equal to V2 squared over 2G. If you were, remember at the beginning of this problem, I said if you're given H and the diameter, you can calculate the discharge by calculating the velocity. So we can take this equation, I believe I put it on the next page. So there's our equation we just developed. Point 1 was here. Point 2 was outside of the tank, but in the free jet. And so we rearrange this equation. V2 squared is equal to 2GH. Take the radical sign, V2 is square root of 2GH. And again, we're going to use this in continuity. That equation is known as the Torricelli equation. It's an equation we use very often. It's also known as the orifice equation. Why? Because you have a free jet issuing from an orifice. We use this in many different engineering designs, this very equation. A leak from a pipe follows this equation. When we design stormwater systems and we want to back up water, we use a small orifice because they're very hydraulically inefficient. So the primary spillway for stormwater systems might be an orifice just to fill up the stormwater system and hold the water back. When we have energy losses, we have to add in some type of a loss coefficient. We're getting to that in this course. So this is the theoretical Torricelli equation, but ultimately we have to face the fact that we do have viscosity, and viscosity is going to lead towards energy losses. But this gives us how to calculate the velocity. So same problem. If we had H equal to 20 feet and D equal to 12 inches, which I think most of you know is 1 foot, then from this equation, V2 square root of 2GH, 2 times 32.2 foot per second squared times 20 feet is 35.9 foot per second, which is a healthy velocity. And therefore the discharge is V2A, which is 35.9 foot per second. Are there any questions on that before I go on? This tank is a conceptualization. All that tank is telling you, you know the energy grade line. Have any of you ever used a pressure washer? Okay, pressure washer, you have a closed tank under pressure. And that's a little pressure gauge in case you didn't know it. That pressure gauge, might be 200 PSI and industrial ones up to 2000 PSI or up to 10,000 PSI. So when we were using a device to clean permeable pavements, it had a big vacuum head and it had jets, and the pressure in the tank was 10,000 PSI. And then what happens is you have this little hole on the side. In the tank, we're holding pressure as an elevation in the open tank. In the pressure tank, we're holding energy as P over gamma. And so you can create pressures that you can create a jet that will cut concrete and steel. And again, this is how we design systems. The part of the design is you may know the velocity you want, what's the pressure you need. Once you know the pressures, you can structurally design the tank. Once you know that, you can then design, well, what kind of a pump do I need to create that? So again, all the engineering designs are connected to basically what we're doing right here. And so when you see in your homework problems or exam problems this open tank, again, all that represents is where you know the energy grade line. And there's a lot of ways to represent that, but that's the most convenient. Okay, oops, let me go back one. So I'm going to have the same system and we're going to add a nozzle because you're going to see nozzles in this system. So you can tell where I ran out of time making up your slides. So here's the exact same system. So if you have a garden hose, same thing. Your garden hose is maybe 1.25 inch, 5/8 inch, and at the very end you put in a nozzle to do the same thing we were just talking about in the last problem. When you look at this system, whenever you see this large tank and a free surface, that's your EGL. That's the Bernoulli sum, right? Whenever you see that, you should know that. Remember, and you had this in fluid statics, you can have a surface in a tank, but if you have a pressurized system, that is not a free surface. In a system like this, that might be your energy grade line because the surface of the fluid in the tank is under pressure. That is not a free surface. If we put a manometer on the side of this tank, the fluid in the tank would rise up to the energy grade line. Okay. I've told you, we've discussed this before. I've just reintroduced it to you. I'll give you a problem on it, and for some reason you want to forget it, but just recognize what you're looking at. Yeah.
If instead of putting a monitor right there, it was just a free jet, would that just create a vacuum?
So if you put a free jet on this, if you're looking at unsteady, what happens with time? Yes, you would create a vacuum. And actually you could create what's called a Mario bottle, in which the only way for fluid to leave after a while is for an air bubble to come in. And that actually gives you a constant discharge system. So that's actually a very specific type of device we use for some instances. So the difference is you're thinking unsteady, and the energy equation was actually developed for steady state. So you shouldn't really be using the energy equation as we've developed it for an unsteady problem. You can certainly apply it as a succession of steady states. So you apply it over a certain time interval and then recorrect the system so the water level drops and therefore the flow changes, next time step, next time step. And that's actually a common way in many of the numerical codes that do, for example, pressure distribution systems. They look at it as a succession of steady states. So here's our nozzle. And again, what's happening is we have this discharge issuing out of the nozzle. The difference is continuity is still operative. And so what's happened is when you go from the tank into the pipe, the velocity in the larger diameter pipe is velocity in this large diameter pipe is much smaller than the velocity in the nozzle. And so what's happening is the pipe leading up to the nozzle is still under pressure. So in the tank, you're storing all of your energy as elevation. Once you're in the pipe, you've now taken the elevation energy in the tank and converted a little bit to V squared over 2G and the rest of it to P over gamma. It's exactly how pressure water distribution systems are designed. We have these water tanks all over the place. And then we have the water flowing in the pipes and we keep the velocities pretty low intentionally. And we store the water as it's moving, we store the energy as the water is moving through the distribution system as pressure. And then at the very end, that nozzle, again, that's the faucet in your home. At the very end, you convert all of that P over gamma in the pipe to remaining velocity head. Question?
The pressure in the pipe would be calculated using delta P equals to gamma delta H
For unsteady problem?
for this.
For this, it's all steady. So if you look at this today and tomorrow, you see the same thing. So this tank is so enormous, we're not draining it. But in reality, how we do systems is we have the water treatment plant typically pumping in at a constant discharge. And we're using water, D is demand, in a diurnal curve. And so what's going into the tank is what's coming out of the treatment plant. So that in real life, these tanks fill and fall. In this problem, we're just looking at a snapshot, and this is the way it always looks.
So to calculate the pressure at that point in the pipe, though, would be.
Right here?
Yes, it'd be, we're not considering it to be a free surface because.
No. So just like in the pressure distribution systems, if you poke a hole in this pipe, the water would shoot up that high in your circulation system. You know, you've got your blood pressure probably really high now, but 120 over 80, that's 120 millimeters of mercury. If you converted that into gamma of blood, it would shoot maybe 3 or 4 feet. So in the free jet, we have atmospheric pressure, and you've converted all the energy to V squared over 2J. And so that's why in many, many systems, there's always a nozzle at the end of the line. And in the piping systems, we have these larger diameters to keep the velocity heads small. I have 6 minutes remaining, and I'm going to do something. I'm going to do a numerical example next time of just energy, but it's going to take about 15 minutes. So instead, let me just introduce mechanical energy. So in this case, mechanical energy is putting energy into a system with a machine. A pump is going to put energy into a system. A turbine removes energy from a system. So for example, here's a pipe. And let's say if flow is from left to right, that might be the EGL if we add no mechanical energy. B1 is equal to B2 is equal to B3. Everywhere we have the same energy grade line. If this is a pump, what does a pump do? It adds energy. And so philosophically, what's happening is we are raising the energy grade line. This is upstream of the pump. And this is downstream. If we select a point here, upstream of the pump, 1, and a point here, downstream of the pump. For no pump, we would say B1 is equal to B2, horizontal line. When we add the pump, Which is larger, B1 or B2? B2 is higher. What a pump does is put in it puts energy into the system. So let's call that energy EP. And if we're going to equate these two, for a pump, the energy is added to the upstream location where you're doing your energy analysis. So again, point 1 is upstream, point 2 is downstream. And what you would say is that the total energy at 1 plus the pump energy is equal to the total energy at 2. So this would be B2 and this would be B1. And the difference between those two is the energy of the pump. What are the dimensions of B? V squared over 2G plus P over gamma plus Z. What are the dimensions of Z? Length, right? The dimensions of B are length. So what are the dimensions of EP? Length. You go to a hardware store and say, give me a 10-foot pump. What do you typically do when you are looking for a pump? They're defined by power. Give me a 0.5 horsepower pump or a 10 horsepower pump. So there is a relationship between the energy of the pump that's going into the energy grade line and power. So if you look at this equation, we've got discharge in cubic feet per second, specific weight in pound per cubic foot. So Q gamma is pound per second, and EP is in foot. So what you have is, for example, foot pounds per second or Newton meter per second, Pascal second. So the units of power are force, length per time. That's the units of power. Q would be the flow, in this case, moving through the pump. Gamma is the specific weight of the fluid that the pump is moving. So that's not so bad, is it? So when you go to the hardware store, or when you specify, you go to pump manufacturers, you specify the pump based on power, but you're basically getting a certain performance. And that performance is a certain discharge and a certain amount of head. And typically EP is looked at, typically, if you go back to the previous slide, you have a constant diameter pipe. What can you say about V1 and V2? V1 is larger than V2.
Less.
Less? This is actually an important concept. Can you have a pump where more flow goes in than out? Can you have a pump where less flow goes in than out? So think of the pump as this box. A pump does not create fluid. So whatever goes in, goes out. So the discharge in and out of a pump is the same. Has to be. If you find a pump that has more water coming out than going in, bring that pump to me. You're creating water, or you're creating that fluid. So if the Q on both sides is not changing, the diameter of the pipe on both sides of the pump is not changing, what would continuity say about the velocity? It's the same. So EP is basically being converted to P over gamma. So the pump, inside the pump, water's spinning around, and inside the pump, you're creating energy as V squared over 2G. As it leaves the pump, it's going into P over gamma. And that's what we typically do with pumping systems. We just keep bouncing up the pressure. That's how we get the water over the Rocky Mountains to Denver. So I know I'm over. Next time, we're going to continue with just a simple energy problem, and then we're going to continue with mechanical energy. Questions from online? Nope. See you Friday. That's right.